Hello and welcome to this lecture series on chemical process modeling and simulation. We've been discussing about modeling energy of systems over a series of lectures. We have had an introduction to thermodynamics. We have derived the criteria for thermodynamic equilibrium. And then we have had a discussion on entropy. And then we have had discussion on three intensive properties, namely temperature, pressure, and chemical potential. Now, in this lecture, we are going to discuss the various so-called thermodynamic potentials. In addition to internal energy of a system and entropy, you have probably come across other thermodynamic potentials such as enthalpy, Helmholtz free energy, and Gibbs free energy. All these will be introduced in this lecture. In addition to molecular driving forces by Dill and Bromberg, I am again including reference books, namely Thermodynamics and Introduction to Thermostatistics by Herbert Callan and Postulational and Statistical Thermodynamics by Y.V.C. Rao. What are thermodynamic potentials? In the Introduction to Thermodynamics, we hypothesize that the state of a thermodynamic system may be determined by its energy. Of course, we define that energy to be internal energy, molecular energy or internal energy. Depending on the nature of the boundaries, depending on the interactions between the system and the surroundings, however, the energy content of the system should be different, isn't it? What we called as internal energy pertained to a specific type of boundary and specific type of interactions. When we say we are saying S or entropy is an independent variable, what we are effectively saying is that I can somehow change the entropy of the system. What is entropy of the system? It is a measure of multiplicity of the macro states. The most likely macro state that you look at it, right? Which macro state is the one that is most likely? The one whose entropy is or multiplicity is maximum, right? And when I am taking a system and subjecting it to a process, I'm saying somehow in this process I can independently change that multiplicity, right? And that requires no heat exchange. Okay, that's why when we have an adiabatic boundary, adiabatic process, you know, there is no heat exchange, and therefore there is no change in entropy. So this is the way we sort of define a boundary, define the nature of the interaction, and define an independent variable. And then we say that the energy of the system is a function of that particular independent variable. So depending on the nature of the boundaries and nature of the interactions, the energy content of the system should be different. Therefore, are there other functions, energy functions, they are also energies, that measure the energy contained or stored in the system? Absolutely yes. Some of the commonly encountered such functions are internal energy, of course, enthalpy, Helmholtz free energy, and Gibbs free energy. They are also called thermodynamic potentials. Please understand they are not to be confused with potential energy. All of these contain both potential and kinetic energy. In other words, there is a contribution of thermal energy, there is a contribution of bond energy, right? Gradients of these potentials represent driving forces for energy exchange, and therefore, from a conservative system standpoint, these energies are called thermodynamic potentials. Now let us, in order to try and understand what these thermodynamic potentials are and how they arise, all right, let us revisit extensive and intensive variables. Why are we doing this? Because remember, as I said, depending on the nature of interactions, depending on the nature of the boundaries, we have to make choices of what is the independent variable, and correspondingly for that particular independent variable there will be a measured energy content, right? And these independent variables are extensive variables or intensive variables. For instance, if you looked at internal energy, the independent variables were S, which is entropy, V, which is volume, and N, which is a measure of the number or amount of substance that is present in the system, right? So these were all extensive variables. Now there are other variables which are intensive variables. For each extensive variable there is a corresponding intensive variable. For entropy it is temperature, for volume it is pressure, and for number it is chemical potential. These intensive variables, if you recall, are the partial derivatives. Dou U, dou S, rate of change of internal energy with respect to change in entropy at constant volume number. Rate of change of internal energy with respect to change in volume at constant entropy and number. Rate of change of internal energy with respect to change in number of moles of the species of the substance at constant entropy and volume. This is how these intensive variables are defined. They are the slopes. If I were to plot entropy versus internal energy versus entropy, the slope would be temperature. This is what we saw when we discussed the physical interpretations of these three intensive properties, right? So these are how we have the independent variables that show up in our thermodynamic analysis. So let us sort of revisit this and then try and understand some of the properties of extensive and intensive variables, and from there we can see, can we make different choices of independent variables, right? So extensive properties in mathematical parlance belong to the class of functions that are known as homogeneous functions of the first order. What are these functions, homogeneous functions of first order? Let's consider a function f of multiple independent variables, x1, x2, x3, so on up to xn. Suppose all the independent variables are increased by a constant factor lambda, then for a homogeneous function of the first order, the function f also increases by the same factor lambda. This is basically a more mathematical way of stating our explanation for an extensive variable. If I doubled my system size, for example, if I double my volume, my internal energy should double. If I double the number of moles of substance present in the system, my internal energy should double. Right? This is how we define extensive quantities, right? So this is exactly what we are talking about. I've just given a general constant factor lambda, and I say the independent variables are in general x1, x2, x3, so on up to xn. In other words, if I were to express this mathematically, so if I have f of each variable being scaled by a factor, constant factor lambda, f of lambda x1, lambda x2, lambda x3, all the way up to lambda xn, right? These are the independent variables. This should be lambda times f of x1, x2, x3, all the way up to xn. So if this lambda is equal to 2, then the function will double. If the lambda is equal to 10, the function will increase tenfold. This is the idea of extensive variables. For example, the volume of water in a glass, for example, is a first order homogeneous function of the number of molecules of water. If the number of molecules of water is doubled under the same conditions, otherwise the volume of water is also doubled. However, I'll give a counter example. In contrast, the volume of a sphere is not a first order homogeneous function of its radius. If you double the radius of the sphere, the volume does not double. Volume is proportional to radius power 3. So the volume increases by 2 power 3, or it increases 8-fold. Right? So this means that volume of a sphere is not a homogeneous function of first order. As a function of radius, v of r is not a homogeneous function of first order with respect to r. So I hope you understand this extensive properties expressed as homogeneous functions of first order. So because of this specific nature of homogeneous functions of first order, they have an important relationship with their partial derivatives. Remember, now we are going to various extensive functions and extensive variables and intensive variables, right? That's where we are heading towards. So we have f of lambda x1, lambda x2, lambda x3, so on, is lambda times f of x1, x2, x3, right? Therefore, if I differentiate both sides by lambda and I use chain rule, we'll get d by d lambda of this f is simply f. Why? Because this is lambda times this function. This function is independent of lambda. So when I differentiate with respect to lambda, I'll simply just get that f. By chain rule, what does this mean? I can express this, right? F of lambda x1, lambda x2, lambda x3, so on and so forth, as the partial derivative dou f dou lambda xi times d of lambda xi. This is the first independent variable. So the change df, if I were to get a differential change in f, could arise due to differential change in lambda x1 or lambda x2 or lambda x3 and so on and so forth. And what I have done is taken that df and then I have used that to construct the first derivative of f with respect to lambda. So by chain rule, this d of lambda x1, the differential of lambda x1, also has now first derivative with respect to lambda. Right? I hope you understand how this chain rule is applied here. Since, of course, this simply is xi, right? Dou lambda of lambda xi is simply xi. So this results in an important relationship. F is equal to xi times dou f dou lambda xi over this sum. Right? This becomes an important relationship. And before we proceed any further, it is important to recognize that the above relationship is not valid for all functions, right? But only for the first order homogeneous functions. Homogeneous functions of first order are extensive functions. And you keep in mind that this f is a function, this f, right? Lambda x1, lambda x2, and so on and so forth, right? So I hope you understand this important relationship between the function itself and its partial derivatives. Okay, so these xi are the so-called extensive properties in this particular situation if I were to apply this to internal energy, and these would be the partial derivatives of the slopes. These would be the intensive properties, right? So there is an important relationship that gets established arising directly from the mathematical nature of homogeneous functions of first order or extensive properties. So let us consider a homogeneous function of first order called internal energy. Right? We have u is a function of s, v, n. So du is the partial derivative with respect to s times ds plus partial derivative with respect to v times dv plus partial derivative with respect to n times dn, and that is given by tds minus pdv plus mu dn. Suppose the extensive properties s, v, and n are increased by a constant factor lambda. Now, before we apply that relationship, I want to ask a question, that the relationship that we derived in the previous slide. I want to ask a question. What happens to these intensive properties T, P, and mu? These quantities. In other words, that the quantity that was in the partial derivative dou f of lambda x1, lambda x2, lambda x3 with respect to dou lambda xi, right? So what happens to those intensive properties? Notice that this is lambda u because I have basically increased everything, all the three extensive variables by a constant factor lambda. So if this is basically u of lambda s, lambda v, lambda n, that will simply be lambda times u. So the partial derivative does not change. In other words, these properties, the intensive properties, remain unchanged by increase the independent variables s, v, n in this particular case by any constant factor. These are the partial derivatives, right? And thus these partial derivatives or the slopes or the intensive properties are called homogeneous functions of zeroth order. So you can increase the independent variables, the extensive variables by any constant factor. However, the intensive variables will not change. That is what we generally use to define intensive properties. Intensive properties are independent of the size of the system by increasing the each of the variables, each of the extensive variables by a constant factor. I'm effectively increasing the size of the system, and that has no effect on the intensive properties, right? Thus these are homogeneous functions of zeroth order. Now that we have understood this, now let us go and apply take internal energy and apply that relationship that we derived between f and the partial derivatives of f. So they result in what are called fundamental equations of Euler. The relationship between extensive and intensive thermodynamic properties may be expressed in the following manner. This is what we found out. F is equal to sigma I equal to 1 to m, where there are m modes, m independent variables. In our internal energy parlance, basically from the state postulate, there are m modes of energy exchange, out of which one is heat and the remaining are work modes, right? So I equal to 1 to m, sum over that xi times the partial derivative dou f by dou xi. This partial derivative I can simply write like this. Now let us apply this here. Xi are the independent extensive properties and the partial derivatives are the corresponding intensive properties. This would result, if F is the internal energy U and the Xi, there are three independent values, independent variables x. X1 could be entropy, X2 being volume, and X3 being number. So we just have S into dou u dou s, V into dou u dou v, plus N into dou u dou n, and that is U. That is your absolute value of the integral value of the internal energy. This would simply, we start with the differential version of this equation. du is, this is just from chain rule, right? TdS minus PdV plus mu dn. This is called the differential fundamental equation of state of Euler. But the other relationship, this relationship is very interesting. U is simply P times S minus P times V plus mu times N. So product of the extensive quantity times the corresponding intensive quantity. So this is the integral fundamental equation of state of Euler. These two equations are called the fundamental equations of state, named after Euler. The first equation is the differential fundamental equation of state. The second is the integral fundamental equation of state. This is of important consequence. All right. And so now you are, those of you who have some background already in thermodynamics can see where this is going to lead to in terms of defining the various thermodynamic potentials, which we will see now. Before going into the other thermodynamic potentials, I want to ask one very important question. Are temperature, pressure, and chemical potential the three intensive properties? If I have n or m number of work energy modes of exchange, then I'll have m intensive properties. Are they all independent of each other? Just as the extensive variables are independent of each other, S, V, N are independent of each other, right? Like that, can I say T, P and mu are independent of each other or not? Let's ask this question. Are the three intensive properties independent of each other? If they are independent of each other, could they be used to specify the state of system? In other words, instead of U being a function of S, V and N, can I say that the energy of the system is a function of T, P and mu? Can we do that? It was stated that the state of the thermodynamic system may be specified or defined by this internal energy. Is it possible to use any of the intensive properties corresponding to each mode of energy exchange to define the state of the system? In other words, can I replace S by T, V by P, N by mu? Can I replace all three by Tp mu? This is the question that I am trying to pose. Let us consider the integral fundamental equation of state of Euler. What does it say? It says that U is equal to Ts minus Pv plus mu n. So if I differentiate U, du is that, since there is a product of two variables, I should write Tds plus Sdt. Similarly, minus Pdv minus Vdp plus mu dn plus ndmu. But the differential fundamental equation of state says that du is Tds minus Pdv plus mu dn. So this term and this term have to add to 0. Therefore, Sdt minus Vdp plus ndmu must equal 0. This is called Gibbs-Duhem equation. This gives a relationship between a differential change in temperature, a differential change in pressure, and a differential change in chemical potential. In other words, I cannot independently change T, P and mu, all three simultaneously, because if I change any of the two, the change in the third one is determined by the Gibbs-Duhem equation. So, to answer this question, are the three intensive properties independent of each other? No. Out of these three, only any two can be independent of each other. The third will have to be expressed as a function of the other two, as constrained by Gibbs-Duhem equation. Therefore, another consequence arises. Can we use the intensive properties to specify the state of the system? Yes and no. It is indeed possible to use maybe one of the intensive properties, T instead of S, P instead of V, mu instead of N. Maybe I can even use two intensive properties in place of two of the extensive properties. However, one can never specify the state of a system exclusively by using intensive properties alone. And that makes sense simply because if I use only intensive properties, there is no independent variable that captures the size of the system, the scale of the system, isn't it? You have to have at least one extensive variable that captures the information of how big is your system. I can say that system A and system B have the same temperature as the ambient temperature, same pressure as the ambient pressure, and same chemical potential everywhere of whatever species, say air. Alright, but there is no way for me to know what is the size of system A and what is the size of system B. If I, however, state either by volume, by entropy, or by number, or by internal energy, at least one of the variables is an extensive variable, then there is a way for me to know for each subsystem A and B what is the size, right? So this is important. So T, P and mu that specification for specifying the macroscopic thermodynamic state of a system is not possible. But if I have at least one extensive variable, that specification is possible. So Tp and mu are not independent of each other and are constrained by Gibbs-Duhem equation. So the most common way in which this Gibbs-Duhem equation, are the constraint of the relationship between these three independent variables Tp and mu. The most common way in which it is expressed is the following. Mu, chemical potential, is a function of temperature and pressure. And this is something that you might have been familiar with if you are a chemical engineer, if you have taken courses in chemical engineering thermodynamics, then you would be familiar with this type of a relationship. And this type of a relationship is very important in understanding phase and reaction equilibria. Now I want you to go back to the previous lecture on chemical potential. So there were these constraints that we derived for reaction equilibria, for example. Okay, so what was stated there was that if we know somehow a model of the system, then through that model, essentially we should be able to derive an expression like this: mu as a function of temperature and pressure. Then using which, and of course maybe other compositions if there are mixtures of multiple species, right? Using which we must be able to predict reaction equilibria or phase equilibria. All the relationships that you've encountered in phase equilibria and reaction equilibria arise out of this fundamental constraint. Okay, so this is an important conclusion that I wanted to draw your attention to. Now we can move on to defining the other thermodynamic potentials. So what are the other specifications of the state of the system that is possible? One specification that we gave was all three extensive variables: S, V, N. Entropy, volume, number. Entropy for heat interactions, volume for moving boundary interactions, and number for permeability and exchange of species interactions. That is one specification that we figured out. And in the previous slide, we figured out that another specification, temperature, pressure, chemical potential, is not possible. Now, what other specifications are possible? So, it was hypothesized, this was the hypothesis starting point, the state of a thermodynamic system, macroscopic state of a thermodynamic system may be defined or specified by U is a function of S, V, and N. So now we ask this question: is it possible to use any one or two of the intensive properties corresponding to each mode of energy exchange, one or two modes of energy exchange, to define the state of the system? For example, is it possible to use sets of variables such as TVN, SPN, TPN? So you know what these are corresponding to. This will correspond to Helmholtz free energy, this will correspond to enthalpy, and this will correspond to Gibbs free energy. All right, but let us see how we get that specification and what it means, what each of those thermodynamic potentials mean. All right, so what does it mean to create such specifications? That we will see in the remaining part of the lecture. But is it possible to use such sets of variables? Yes, absolutely yes. Before answering this question, observe that the question requires that we have to be able to maintain this set of variables fixed. And once again, I want to draw your attention to the fact that this depends on the nature of the boundaries and the interactions between system and surroundings. So when I am making a choice of a set of independent variables, I am effectively making a choice on the nature of boundaries, and I am essentially making a statement about the interactions between system and surroundings. In the internal energy formulation, excuse me, in the internal energy formulation, U was stated to be a function of S, V, and N. Here, this means S is fixed by an adiabatic boundary, V is fixed by a rigid boundary, and N is fixed by an impermeable boundary. When there is an adiabatic boundary, there is no heat exchange. Therefore, ds is 0, S is constant. If there is a rigid boundary, dV is 0, V is constant. If you have an impermeable boundary, dN is 0, N is constant. This is how we fixed these three independent variables, and we stated that we hypothesized as a starting point that the macroscopic state of a thermodynamic system is characterized by some energy. We called that as internal energy. That was the name that we gave. So how do we fix temperature or pressure of the system? Those are the ones that we are trying to change now, right? So to answer this question, how do we fix the temperature or pressure of the system? We go to the criteria of thermodynamic equilibrium. The criteria of thermodynamic equilibrium answer this. Temperature is fixed by a diathermal boundary. What did we find out? When we changed the adiabatic boundary to a diathermal boundary, the criterion for thermodynamic equilibrium was that temperature has to become fixed. When we change a rigid boundary to a moving boundary, what did we find out? We found out that instead of volume, now what has to be fixed? The criterion for thermodynamic equilibrium is that the pressure has to become fixed. So the criteria for thermodynamic equilibrium answer this question. What does it mean to change these specifications of what the appropriate independent variables are? I hope you understand this clearly. So again, note that we cannot choose Tp mu because they do not form an independent set. Gibbs-Duhem equation relates them. It is interesting that there has to be, therefore, at least one independent variable corresponding to any one mode of energy exchange in our specification of the state of the system, so as to capture the size of the system or extensivity. This was something that we discussed. It may be shown that all these specifications of the state of the system are equivalent. What I mean by this, whether I say U is U of SVN or S is S of UVN, or I'm going to put the cart in front of the horse and say when I change volume to pressure being the independent variable, right? When I do that, then the corresponding thermodynamic potential is enthalpy. So H is H of SPN. When I change temperature as the independent variable instead of entropy, then the resultant thermodynamic potential is Helmholtz free energy, which is denoted by the symbol A. So A is A of TVN. When I change both entropy and volume as no longer independent variables and instead choose temperature and pressure, of course with N not mu, right? Then I get Gibbs free energy, which is denoted by this symbol G. So G is G of TPN. So there are these 5 specifications: internal energy specification or formulation, entropy specification, enthalpy specification, Helmholtz energy specification, Gibbs free energy specification. All these specifications of the state of the system, macroscopic state of the system, are equivalent. In other words, they all contain the same extent of information about the state of the system. And this can be proved using tools of postulational thermodynamics or even using statistical thermodynamics. Proof is available in any of those references that I mentioned initially. Thiel and Bromberg's Molecular Driving Forces, Herbert Callan's Thermodynamics and Introduction to Thermostatistics, and Y.V.C. Rao's Postulational and Statistical Thermodynamics. In all these 3 books, there are the proofs are given, but we are not going to discuss that in any detail here. So, but what are we doing when we specify? I'm sorry, there has to be a what here. But what are we doing when we specify the state of system by say TVN instead of SVN? I have chosen temperature instead of entropy. What have I said? From the criteria of thermodynamic equilibrium, I mentioned that the boundary has been changed from, nature of the boundary has been changed from an adiabatic boundary to a diathermal boundary. That is from a physics standpoint. Now from a mathematical standpoint, what are we doing? Instead of specifying the heat exchange, the mode of energy exchange is thermal energy or heat, by the entropy of the system, we are now specifying heat exchange by temperature. What is temperature? Temperature is the slope that is given by this partial derivative. So if you go back to the original first slide which we had revisiting extensive and intensive variables, f is equal to f of x1, x2, x3. Now instead of specifying the independent variable to be x1, that would have been s, entropy. Now I am specifying the extensive variable to be dou f dou x1 at constant x2, x3. I am specifying it by the partial derivative, which is temperature. This is what I am trying to do from a mathematical perspective, right? So we need to sort of figure out how to go from one mathematical specification to another mathematical specification. This is the piece that remains to be figured out, and once we figure this out, then we will automatically get what are those thermodynamic potentials, meaning what is enthalpy, what is Helmholtz free energy, what is Gibbs free energy. From a physics standpoint, what am I saying is that an adiabatic boundary is changed to a diathermal boundary, right? But from a mathematical standpoint, I am replacing an extensive independent variable by the intensive partial derivative, which is the slope. So let us see how to go about doing this transform from one variable being the independent variable to another variable being the independent variable. This is like a coordinate transformation, isn't it? Now I am changing my independent variable. Suppose I have y as a function of x. Now I am changing x to be something else. What am I changing x to be? I am changing x to be the slope dy by dx, right? That's what I am doing effectively. So this transformation of coordinate system, right, will give us the answer to the question, what is the resultant energy? Remember, the hypothesis is still that the macroscopic thermodynamic state of the system can be specified by or defined by its energy. Which energy is it? We are going to see. This is given by what is called Legendre transforms or Legendre transformations. This is like a coordinate transformation. So we will take a short detour into how Legendre transformations are constructed, right? And we will work out one simple example of Legendre transformation so that we can understand how to go from an extensive first order homogeneous function as an independent variable to an intensive zeroth order homogeneous function as the independent variable, right? This is the goal. Hello. We had said that we will discuss Legendre transforms and how using Legendre transforms, thermodynamic potentials, the various thermodynamic potentials, enthalpy, Helmholtz free energy and Gibbs free energy may be derived. However, I am observing that this lecture is already more than 38 minutes long, and therefore I have decided to split this lecture into two parts. So I have I'm closing the first part with this slide. So if there are any questions, you can always approach me, contact me through the YouTube channel, or reach me over email or other modes of communication. I'll be very happy to answer your questions. The second part of this lecture, starting from what is Legendre transform, how is Legendre transformation obtained, and then with some examples of converting a function to its Legendre transformation and inverting the Legendre transformation back to the original function, followed by the obtaining of the various thermodynamic potentials, will be discussed in the subsequent part of this lecture. Thank you very much for listening to this lecture. Have a wonderful day.